Today, we're going to begin a very fundamental and important topic in engineering, which is nothing but control systems. Before we jump into control systems, let's start with something even more basic. What exactly is a system? A system is a setup that takes an input, performs some process or operation on it, and then gives an output. Let's take a toaster as a simple example. The input is a slice of bread. The process is the heating inside the toaster. The output is a toasted piece of bread. You give the bread as an input, the toaster heats it for a set time is the process, and you get a crunchy golden toast as an output. This is a system. It takes input, processes it, and gives output. In electronics and embedded systems, we often call devices like ESP32, Arduino, or Raspberry Pi a system because they have everything built in. They can take data from sensors, process it using a microcontroller or processor, and then give a meaningful output like lighting up an LED, sending data over Wi-Fi, or controlling a motor. So, in short, a system is a complete setup that senses, thinks, and acts. Now that we know what a system is, let's move to something more powerful, a control system. A control system is a special kind of system that not only takes input and gives output, but also keeps checking its own output too. Make sure it's doing the right thing. And if something goes wrong or changes in the environment, it automatically fixes itself. It's like giving a machine a goal and then letting it take care of everything, measuring, comparing, adjusting all by itself without needing you to correct it every time. Let's now take a real world example that almost everyone here has heard of, and that's the Tesla Autopilot system, which is a great way to understand how a control system actually works in practice. Let's imagine you're sitting comfortably in your Tesla on a highway and you activate the autopilot feature. The first thing you do is set the car's desired speed, let's say 100 kilometers per hour, and this target speed that you've just given the car becomes the input to the system. That's what the system is supposed to achieve and maintain. But Tesla doesn't just hit the accelerator and hope for the best. Instead, the vehicle is equipped with a combination of advanced sensors, including front-facing cameras, ultrasonic sensors, and radar, all of which work together to constantly observe the car's surroundings in real time. These sensors gather data about everything happening around the vehicle, from the speed and distance of the car in front to lane markings, road curves, obstacles, and even traffic signs. And they send all of this information to the car's onboard controller, which is basically the electronic brain of the car. Now, the controller takes this incoming data and immediately compares the current situation. For example, your car's present speed and the distance from the vehicle ahead, with the desired speed you had set earlier, which is 100 kilometers in our case. If the controller notices that the car in front of you has suddenly slowed down or moved too close, it decides that continuing to drive at 100 kilometers could be dangerous. And based on this decision, the controller sends an appropriate signal to the actuators, which are the parts of the vehicle that physically carry out actions like reducing throttle or applying brakes. As soon as the actuators respond and the vehicle's speed begins to drop, the sensors don't stop working. They continuously monitor the new speed, the updated distance from the vehicle in front, and all other relevant surroundings, and send this fresh data right back to the controller. This updated information is what we call feedback. The controller again compares this new feedback with the original goal, the target speed of 100 kilometers h, and decides whether the current situation is now safe or if more adjustments are needed, and if necessary, it repeats the process, adjusting acceleration, applying or releasing brakes, and so on. This entire cycle of sensing the environment, making decisions based on real-time data, performing physical actions, and then rechecking the result happens continuously and automatically, many times per second without any human involvement. And this is what we refer to as a closed-loop control system. In simple terms, Tesla Autopilot is not just blindly following one instruction. It is constantly checking, comparing, adjusting, and then checking again, all in a loop to ensure that the vehicle behaves exactly the way it's supposed to, even when external conditions change suddenly, like another vehicle cutting into your lane or unexpected slowing of traffic. This continuous feedback loop is what makes the system intelligent, responsive, and safe. And that's the key difference between a normal system and a control system. The ability to self-correct and stay in control no matter what's happening outside. That's all for today's video. In our next video, we will dive deeper into the different types of control systems, what they are, how they differ, and where they are used in real life. So don't miss that.